Shifting to the lecture, we shall be talking here about refraction of light. Now, we talked last class period about reflection. And reflection is, of course, something we're very comfortable and familiar with. Refraction, I'm sure that some of you, well, at least I'm guessing some of you, don't have any experience with even the word refraction. Refraction, as illustrated in this picture, is a bending of light when it goes from one material to another. You often don't think about that happening, but here's something that we do think about happening. You know, my sister lives in Huntington Beach. I love to go there all the time, whenever I can. And you have people who are jogging up and down the beach. And some people will jog on the concrete walkway. Now, if you're jogging on the concrete walkway, you can make pretty good time. But if you go into the sand, what happens to the speed when you go into the sand? You slow way down. So let's suppose that you're just jogging along and all of a sudden you get into the sand. That really slows you down, but it also changes the direction you're going to travel. It pulls you back on the side where you step into the sand and it twists you. And you end up going a different direction when you go into the sand. And that's exactly what happens with light. When light is going from a faster medium, like air, into a slower medium, like glass, it gets pulled into the slower medium. Now, I say it gets pulled. This here, whose principle are we talking about if we're drawing these little wave fronts from points on little spherical waves from points along the wavefront? Whose principle is that? Whose principle is it that you could treat each point on a wavefront as a point source for a spherical wave? Huygens principle. So this is using Huygens principle. When I have a wave going through air, the wavelength is pretty big. When it goes in water, because the speed of light in water is slower, the wavelength is smaller. And so what ends up happening is, when it goes, like right here, you would have a wavefront that would be this big radius here, and then like that in there. And so the waves don't travel as far in the liquid, causing it to change directions. Now, I have some pictures that I think are going to be a little more illustrative, but it's important that we note, just like with the wave on a string, if I have two strings tied together, and one's a fat string and one's a thin string, we learned that the speed of a transverse wave in the string is equal to the square root of the tension divided by the lineal density, so that the speed goes slower in the fat string. So if I have a wave going there and I have the two strings tied together, I'm going to have the wavelength change because it'll have to have a shorter wavelength on the fat string with its short speed or low speed. But the frequency, the time to go up, down, has to be the same for both strings. Why? Because the place where they're tied together would break apart if you had a different frequency on one string compared to the other. And the same is true for waves, for light waves. If I have a light wave, that light wave is going to remain the same frequency no matter what I do with it. The wavelength can change, but not the frequency. So light goes from air into water, the frequency stays the same, but the wavelength is going to shorten up when it goes in water. So this is the picture I put on the first page. Obviously this one. I am more aware of the lack of perfect lines here, given that they are perfect lines. I'm not going to show you what it looks like on mine, but those jaggeds make me unhappy. The picture on the left is showing the incident ray. Remember, we started saying geometric optics, talking about rays of light. The incident ray coming in, and because the wavefronts bend, it's changing direction. and staying with this, you saw Snell's law. Snell's law is the mathematical law that we use to explain, or to describe, not explain, but to describe that change in direction. So the red lines on this picture are what we need for the geometric determination of Snell's law. We have light coming in on the incident ray. It refracts. Refracting is bending when it goes into material with a different speed. To go on this transmitted ray, and we measure angle of incidence and angle of refraction. Now, before we measure angle of incidence and angle of reflection, how do we measure the angle of incidence? From the surface normal to the incident ray. And how do we measure the angle of reflection? From the surface normal to the reflected ray. We have to do the same thing here. Now, honestly, with reflections, we could have measured from the surface to the rays, and we would have had right answers. But for refraction, for Snell's law, it makes a difference. So that's where you have to be careful. We measure the incident angle as the angle from the surface normal to the incident ray, and the refraction angle is the angle from the surface normal on the other side of the surface to the refracted ray. And so you can see the incident ray and the refracted ray there, the blue rays. And then this is one wavelength in air between the wavefronts, one wavelength in water, or glass, excuse me, for the two wavefronts, and then just did some geometry. So we have, I totally need to change colors. This line here is the same line in both of the two triangles defined by red lines. It's in fact the hypotenuse of both of those. And so looking at that, having the hypotenuse being the same, sine of the angle of incidence is going to be the opposite side, the wavelength, divided by the hypotenuse, which is the same for both. So sine for the angle of incidence is wavelength incidence over the hypotenuse. Sine for the refracted angle, the transmission angle as it's called here, is the wavelength in the glass divided by that same hypotenuse. So if I just divide one sine by the other sine, the hypotenuses, I don't know if that's the correct term or not for the plural of hypotenuse, which is sad. I mean, probably is hypotenae, but I don't know. I tend to be really anal about these things. Just for the record, what is the plural of forum? It was good for a laugh. It's fora, right? Plural of appendix? Appendices. It's actually not. Plural of octopus is octopodes. Because I tend to be really anal about this. Unfortunately, the English language is one of those dynamic languages. If people say it wrong enough times, it becomes accepted. So you can say appendixes. People say, okay. You can say forums. People, oh, okay. We put S on the end. We're American.
So what do you think?
Fora, yeah.
Plural of hippopotamuses.
I actually looked this up this week, so I should know the answer. And it seems to me that it is hippopotami. There's also hippopotamuses, but that is using the incorrect, we're American, we put S's at the end. Okay, that was a non-useful tangent. I used to try to keep the tangents useful to the topic. Okay, so we have this ratio between the sine of the incident angle and the sine of the refracted angle, and the wavelength of the incident light and the wavelength of the refracted light. Since wavelength changes, we don't like to leave this with wavelength in there. And so we take our relationship that wavelength times frequency is equal to the speed of light, and we say, then that means wavelength is equal to speed of light over the frequency. The frequency is the same for both, So that's the same, and then we just have that speed of light that's going to be different. But here's where things get most interesting. We talk about, instead of, and you can go through the math steps here. I'm not super interested in going through the math steps because they're simple. This here is what we get for Snell's law, where we have a new definition. N is equal to the speed of light in vacuum divided by the speed of light in the material. C, remember, is always the speed of light in vacuum. V is the speed of light in the material. So N is called the index of refraction. Quickly, what's the plural of index? Indices. Excellent. Okay, so the indices of refraction, I'll show them on 2 slides from now. The index of refraction, by its name, that has meaning. Index of refraction means it's the number that tells you about refraction. It has a very descriptive name. Refraction, the bending of light when you go from one material into another material. And what is the fastest material for things to travel through? Vacuum. That's the only thing I've told you about speed so far. Vacuum has the fastest speed. So if I'm going through something like glass, the speed is slower. If my speed is slower than c, what does that make n? Greater than 1. So indices of refraction are always 1 or greater. Index of refraction for vacuum is 1. Air is approximately 1. Everything else is greater than that. So if you see the index of refraction, you can determine the speed. Now let's just take an example. Diamond. N equals 2.42 if I remember correctly. What does that tell you about the speed of light in diamond? It's slow. How fast is it? I'm asking for a very simple equation. That is the exact speed of light in vacuum, 299792458. If somebody discovers differently, what they've done is refine the measurement of the meter, because that's considered exact by science. So what do we get?
1, 2, 3, 8, 8, 1, 1, 8, 1.
And I'm going to put 1.2, you said 388?
Yeah.
I actually put one too many significant digits, right? We only have 3 significant digits, so it should have been 1.24 to maintain the number of significant digits. So the speed of light in a diamond is relatively slow. Because the speed of light in a diamond is relatively slow, if we look at this equation, if we have light going from air into diamond, so if I'm going from air into diamond, then I'm going to have n air sine theta incident is equal to n diamond sine theta transmitted. And that means that sine theta transmitted has to be n air over n diamond sine theta incident. What is the maximum value that sine theta incident can have? 1, right? Sine goes between -1 and +1. And in fact, your incident angle has to be between 0 degrees if it comes in normal to the surface and 90 degrees if it comes in parallel to the surface. So for angles between 0 and 90 degrees, the maximum value you can possibly get for sine theta is 1. If sine theta is 1, we actually call this the critical angle. Well, let me not talk about that yet. It's the last slides of today. If sine theta is equal to 1, then sine theta transmitted is equal to 1 over 2.42 Therefore, what is the theta transmitted? It's what? Equals 24.4 degrees. So if you have light going from air into diamond, the farthest away from the normal it can be is 24.4 degrees. And that would be if you were coming parallel to the surface. If you're coming more into it, it's going to be even closer to the normal. Things to learn from this. Number one, light always refracts toward the normal if you're going into a slower material. Number two, diamond with a very slow speed, it's always coming reasonably close to normal. That's actually a big thing. Why are diamonds considered pretty? They're sparkly. And why are they sparkly? Because the light comes in, goes close to the surface normal, so they put the faces on there to get the directions the light's going to go in. And then they have the back cut with a certain shape so it'll bounce around. And it will only come out from certain locations. And so you get, essentially the light is really concentrated. It comes out, it only comes out at certain angles. And so it sparkles because it's concentrating light and only giving off at certain angles. And that's why it's a pretty gemstone. That and monopolies have made them very valuable. They also have really good properties, thermoelectric properties.
But I don't think people are buying them for that reason.
That's right. People do not put them on their fingers because of the good thermoelectric properties. When you look at this equation, notice that it's symmetric. That is, the left side and the right side look exactly the same except for the indices have changed. That means that light goes the same if it's going from air into water or water into air, it'll be the same path. Right, so if light comes down this path and then goes into water like this, if I reversed it from the water went like this, it would come out on the same path. So light goes the same forward or backward. That's an important thing about light. You can reverse light and it still follows all the rules. So in optics problems, we can work from the end to the beginning or the beginning to the end because it works the same both ways. So how do we solve problems like Snell's law, or ones involving Snell's law? I was going to quote the song like Maria. Okay, you have to make sure you measure the angles correctly if it's a refraction problem, measuring from that surface normal. Once you have those angles from the surface normal, you just apply the Snell's law equation with the indices of refraction, and you get your answer. So it's easy to solve these problems. Notice these are the laws of refraction. That this here is just the same as in the laws of reflection that you have. The angles for incidence and transmission are in the same plane, the plane of incidence. But if it's transmitted on the opposite side of the interface. If it's reflected, it's on the same side. So this is showing both reflection and transmission. Let us have a clicker question. Light moves from diamond into air. How does the speed of light compare in these two materials? I expect 100% here. Okay, Sally. Okay. We were close to perfect. Light does definitely not have the same speed in both diamond and air. Light goes significantly slower in diamond. That's what that index refraction tells you. The 2.42 means it's 1 over 2.42 times as fast in diamond compared to an air. Or air is 2.42 times faster than in diamond. Yes?
Is that related to density, or what is it related to?
It is not strictly density. It has to do with the absorption re-emission, and I can't really explain any further than that. It's not strictly density, though. Okay, so here are some indices of refraction. Yes, sir?
Just kind of jumping back a couple slides, you were saying that if it was the sine of the incident was 1, then it was going parallel to the surface?
Yeah, because 9 degrees, sine 9 degrees is 1.
So how does that even translate into going into the...
Well, in theory, you could be infinitesimally close to 9 degrees, and so that's the limit. Okay, here's indices of refraction of common materials. Air, 1.000293. What does that tell me? It tells me the speed of light in air is essentially the same as in vacuum. It's ever so slightly slower. You know, 0.0029%, something like that. No, 0.029%. I can do math. If you look there, you'll see hydrogen has an even faster speed than air. The fact is, the speed of light in air depends on temperature. Should we get to my last slide today, which we should actually, I only have like 15 or so, we'll talk about mirages, and mirages occur because when you heat up the air, you have a faster speed of light, and so that causes refraction. That's the root cause of mirage. So we have a couple gases there. You see all the gases, very high speeds. Then we go into, now all of those gases, there are some gases with lower speeds. Then we go into things that are liquids, and you see benzene, carbon disulfide. Those have indices of refraction somewhere between 1.3 and 1.7. Our eyes, we have aqueous humor and vitreous humor. Those are both essentially water. They're like 1.34 or something. They're very close to the speed of light in water. Then we have solids, and of course you see the diamond value, 2.419 there. And you see a range of things. Ice, 1.309. Ice is pretty fast speed compared to most things. And you can compare. Now glasses. We have here crown glass, flint glass. We don't have on here sapphire. I did my master's degree research on sapphire, which is a very clear, transparent glass. And it has a slower speed. It's like 1.76, I think, is the index of refraction for sapphire. So it's a little slower. And of course, diamond is also a transparent, but it's not a glass like sapphire. And 2.4, actually, sapphire is technically a crystal. We just consider it like a glass. We use sapphire on things like our iPhones to make the little buttons stronger. Hopefully they'll make the screens out of sapphire eventually when it gets cheap enough. Sapphire you can grow, so it's not super, super expensive. It is expensive compared to other things. And just in case you're wondering, a lot of people say, what? When I say sapphire is perfectly transparent. It has no color. That's because most of the times when you see sapphire, it has a dopant in it, an impurity. And impurities are what give most of your gemstones the colors. So, for instance, if you put chromium impurities in sapphire, then the sapphire takes on a pretty pinkish color. We actually have a gemstone name that's different for that. We call it ruby. Ruby is just sapphire with chromium. And then if you put iron in, it'll give you, other colors like blue and green. Okay, this here is present for us to just observe and appreciate the different speeds of light in different materials. I only have 13 slides. I'm well on my way. So a problem, something to allow us to use our newfound information. A beam of light strikes one face of a window pane with an angle of incidence of 30 degrees. The index of refraction of the glass is 1.52. What other material am I dealing with besides glass? Air, right? You have to make that assumption. What do you use for the index of refraction of air? Yeah, to 3 significant digits, it's 1. So you just use 1 there. The beam travels through the glass and emerges from a parallel face on the opposite side. Ignore reflections. Find the angle of refraction of the ray inside the glass and show the rays in the air on either side are parallel. Now, before we do that, let's do a demonstration to see if it really does what they say it's going to do. Jerry, you want to do like you did before? Yeah, have Toussaint help you again. Apparently the magnets are not perfect because this is slipped. Actually, well, the other ones make it darker. There are two of them, a darker one and a lighter one. The one in back is the dark one. Don't worry about it. That one's got a problem. Don't worry about it. Yeah. Okay, we'll just deal with that. It's dark enough. So here we have the beam coming across the board. And I'm going to use a piece of plexiglass, which has an index refraction of just about 1.5, so it's virtually the same problem. I put it in here. Now first I put it in so it's angle of incidence. What would you call the angle of incidence right now? Okay, 0, because the normal is pretty much parallel to it. Now if I tip it, first thing you notice is I got a reflection there. In fact, I have two reflections. Why do I have a reflection on a nice glass surface? It's smooth. Whenever you hit an interface, you're always going to have some reflection, unless they have exactly the same index of refraction. And so I have a reflection here. There's a second, weaker one up above. How do I get the second one?
What is your second one?
The second, I know if you're farther away, it's hard to see. There are two of them, one on the inside of each finger right here.
Is the second one from the reflecting on the X-ray side?
That's right. The first one was light reflected off of the front surface. The second one, light went in, it transmitted. As it went in, it refracted, so it changed angles. Then it hits the back surface, and when it hits the back surface, some is reflected and some is transmitted. The transmitted on the back side came out here. The reflected came up here, and of that reflected light, some was transmitted. Now, it turns out that in this case, I probably have about 5% of the light that's reflected off of each surface. So the intensity of this one here, the first one is about 5% of the intensity of this light here. So I had about 95% that goes through. About 5% of that 95 is reflected back, which is pretty close to 5% still, right? And then about 95% of that was transmitted here. So this one's about 5%. This one here is going to be 5% times 0.95 squared. So let's just ballpark it and say somewhere around 4.5%. So there's not a big difference in the intensities of these two. When we talk about interference and what makes like colors in bubbles, colors in bubbles, or colors in a thin layer of oil on water, because these reflections are very close to the same intensity, things work out okay. If one was much brighter than the other, it wouldn't make much difference. There should also be a very weak reflection on the backside from this one here. But that's going to be, the reflected amount is going to be about 5% of 5%. Well, that's a really weak reflected amount. And so that's why we don't see any more. We only see those three. So now we're starting here. I just tipped a little. We want to go to an angle of 30 degrees. So there's my angle of 30 degrees as well as I can do. And the question says to show that this is parallel to that. Now let's check and see even if that's true. How can I check and see? Well, I'll mark a point here, point here, point here. Okay, so I marked points on that line. to see how that transmitted line goes, take this out and mark points on this line. I'm trying not to mark on my initial points, which made me go too high. I'll just go in between. That was too low. And now if I turn on the lights, we can check to see if, in fact, is the upper line parallel to the lower line? If you look at the data points, it's kind of hard to see because of the spread. I didn't want to put them on top of each other because they appear on top. But indeed, this lower line, defined by this point, this point, this point, and this point are the lower ones, is consistently just a little below the points on the upper line. And so we have experimental evidence that the problem was correct in its statement. So now let's go back to that problem. And try to work it out. So I have a beam of light that strikes with an angle of incidence of 30 degrees, and the glass 1.52. What's the first thing I should do to do this? Draw a picture. So I'm going to draw a picture. I'm going to start by making my glass. There's my glass. Actually, you know what? I'm going to rotate it. My glass is going to be like this. And then I'm going to draw my incident rays. So my incident ray goes something like that. Now I need to have my surface normals. So I'm going to draw two surface normals. That one for the first surface and this one for the second surface. And now I'm pretty much ready to go. I just need to mark a couple important things like this angle here was 30.0 degrees, and this was N2 equals 1.52, N1 equals 1.00, N3 equals 1.00. Now that blue line is what would have happened if the light had just gone straight. Now we need to calculate what really happened. So when it hit the first surface, what happened? It'd be refracted. And which way is it going to be refracted? Toward normal. Because it's going from a faster to a slower medium, it's going to be refracted toward normal. So my refracted ray is going to do something. Okay, that didn't start the right place, sorry. My refracted ray is going to do something like that. And I'm going to have my index, or not my index, but my refracted angle right there, theta 2. How big is theta 2? Calculation, I have to use Snell's law. So I'm going to put N1 sine theta 1. I didn't label that, equals N2 sine theta 2. I want to solve for sine theta 2, so I divide both sides by N2. So theta 2 is equal to my N1, well, first put arc sine. Now we can put the numbers in here pretty easily. Inverse sine of 1.00 over 1.52. Sine of 30 degrees is 1/2, so times 0.5. And then I need people with calculators to give me a number. 19 point what? So this angle that I labeled theta 2 is 19.2 degrees. Now I have that angle theta 2. I have a new place where the light is hitting, right? My second set of normals was a foolish thing to do because it's the wrong place, because that's not where the light is really going to exit. It's going to exit over here. So I will make a corrected surface normal, maybe. A corrected surface normal that goes here. And so where is the angle of incidence for that second surface? Okay, it's going to be this angle there. Now how does that angle compare to the first theta 2? It's what? It's the same. Why is it the same? Okay, from parallel lines, right? If this side here was not parallel to that side, if the front side and back side weren't parallel, those wouldn't be the same angle. It's only because they're parallel surfaces that's the same angle. And so then I have this here I will call theta 2 prime. You can't see the prime, but theta 2 prime is equal to theta 2 because they're parallel surfaces. And then finally, my refraction angle. How do I find angle 3? Snell's law again. So I now put N2 sine theta 2 prime is equal to N3 sine theta 3. But notice N3 is the same as N1. And sine theta 2 prime is the same as sine theta 2. So this is the same as N2 sine theta 2 and N1 sine theta 3. Well, I won't just jump to the answer because I'm guessing people didn't follow everything I said. If you put in your numbers, that's going to be .2 degrees. You do that inverse sine, and you're going to get back what angle? 30 degrees. Because it exits at 30 degrees, that's my evidence that it's parallel. So now I can draw the last portion of, whoops, forgot to turn on the line. The last portion comes out like that at the same angle as my original light. Why do I do a practice problem? Well, so you can see the ideas put into play. Was this a difficult problem? Nope. Nope, it wasn't difficult. But it's new ideas we had to go through. We found the angle of refraction of the ray inside, 19.2 degrees. We found that theta 3 was equal to 30.0 degrees, which was equal to theta 1, and that's why they were parallel. Next slide, please. Okay, to the mirages, as Bugs Bunny calls them. How many people have seen a mirage? Okay, so hands are slowly coming up. Mirages are caused by refraction. Now, my first experience with a mirage, we're driving down the road in the middle of like Flagstaff or somewhere where it's blazingly hot. And I look at the road up ahead and I see water. And I'm like, sweet, that means it's going to be cooler up there. And as Tori just said, no, I was wrong. I was excitedly waiting for us to splash in the water, wondering what was going on, and we never hit water. If you watch Bugs Bunny cartoons, it's not exactly what Bugs sees, is it? What does Bugs see? You guys haven't watched? Well, Bugs sees an oasis with a palm tree and a lake. Over and over and over again. And then Bugs goes and dives in and takes big mouthfuls and then realizes, no, it's just sand. Now, what was I seeing when I thought I saw water on the asphalt ahead? Because it clearly wasn't water. What was I seeing? Not a reflection, a refraction of the sky. Light from the sky was coming down and bending back up, and my eye just extrapolated and said that was coming from the ground because of the direction I was looking. And so I was actually seeing the sky down on the ground. Now, of course, the big question is, how does that happen? And so we have here an illustration to try to, ooh, that was not good. Try to indicate what happens. First of all, you have very hot air near the ground. And you have cooler air up above. The light goes slower in the cooler air, faster in the hot air. And so as the light comes down from the sky, or as the picture shows, the tree, as it comes down, notice we have the wave fronts and it's showing wavelets coming out, and the ones down below have a larger wavelength, hence they go out further. And so the new wave fronts are constantly changing angles. And so the light comes and it changes angles and comes back up because of the gradient change, continuous change in the speed of light as you get closer and closer to the surface. So you can, as illustrated in the upper picture, you can see a tree in a mirage. But when you see that tree, what does it look like? It's going to look inverted in the mirage. So the Bugs Bunny version of the mirage with a palm tree up there, that doesn't work because the tree should have been upside down if he was really seeing a mirage. And that would have been a tree further on. If there was a tree further on, he would have been good. That's not the only kind of mirage you can see. I think I have another one here. Yes. You can also see upside down mirages. Here you have a figure showing a photograph taken of a mirage. Going back to this one, I had to have the light bending, and it bends away from the hotter region. When I have a mirage, it bends away from the hotter region toward the colder region. So it's normal when you have a road, if that road is made out of something like black asphalt, black absorbs really well. And so it absorbs a lot of solar radiation and gets hotter. And so the road surface is very hot, and so the air right above it's going to be very hot. That's why that's the hotter region, it bends away from it. So how do you get this kind of mirage? Well, you have to have warmer up above. How do you get warmer up above? There are two reasonable situations where this occurs. One is over a body of water. A body of water will tend to make the temperatures cooler because of evaporation, and also because water has a very high specific heat, so it doesn't change temperature very quickly. So you have a cooler temperature above the water and a warmer temperature up above. And so if you have that situation, you might look out above the lake and you see a sailboat sailing upside down in the sky because you had light from that sailboat came up, hit the hotter air and changed direction and came back down to you. Or you could have it if you have the right situation where you have like a mountain a city, and then something over here. And you tend to have air temperatures that are consistent there, and it could be cooler down here in between. Hot air is going over there. So that's another situation that can cause you to have a mirage that's up above. I've never seen that kind of mirage. If you ever drive from here to California and you go through Utah, what's in Utah? Have you made the drive? What's in Utah? Once you leave Salt Lake City, until you get to Wendover, what do you see? Nothing. You've got some salt flats. Off in the distance you have some mountains. And pretty much every time I've driven through there, if you look north toward the mountains, you'll see a mirage on the salt flat between you and the mountain. So that's a great place for seeing mirages. You tell your family, yes, we need to drive to California so we can drive through the middle of nowhere called Utah and see these mirages. So, wow. Yeah, I was going to say, wow, we're almost done with the lecture. Yes, we're also almost out of time as well. Refraction of light. You guys have seen this. This is not anything to do with Pink Floyd. It is simply light being spread out or dispersed by color. When I was a kid, my teacher got some prisms for the classroom, like second grade. And if we finished our homework early or our classwork early, we could play with the prisms. Woo, woo. And most of my classmates took the prisms and held them up to sunlight and said, ooh, pretty colors. I did something completely different. I put them up to my head and tried to walk around with everything flipped upside down because apparently I was a different child. Let's talk about, once again, why this occurs. So, I'm just going to turn that off. I'm not going to come back to it. I have light coming out of this. If I go through a prism, I have light that's going to do what when it hits the first surface? It's going to refract and reflect. When it gets to the second surface, it'll do the same. So now if you look at this, I have light that's coming in reflecting. You can see the light refracted. It changed angles going through my prism. And then it comes out and refracts again. By the way, notice something cool. Here the light is as steep as it can get. It goes closer and closer to horizontal, stops, and then starts going steeper again. There is actually a minimum deviation that's possible in the middle here. Notice this is most definitely not parallel to this. Why? Because the surfaces aren't parallel to each other. So, the question we started with was, why are the colors spread out in the picture? It starts with a simple fact. We learned that the speed of light is different in glass than it is in vacuum. Well, it turns out while the speed of light is the same for all colors in vacuum, if you're in something besides a vacuum, the speed of light varies by color. But if the speed of light varies by color, that means the index of refraction varies by color, which means that the angles of refraction vary by color. And so you tend to have the colors with the higher speeds are going to be refracted more. The ones with the slow, or excuse me, I said the other way around. The ones with the higher speeds are refracted less. The ones with the slower speeds are refracted more. And so you get different colors. Now, why don't I have any spread in color here? Because it's only one color. If I had a white light contains a large spectrum of colors, then I would see the colors spread out. Now this here, well, it's kind of cool, right? And you can see reflection inside here. If I go like this, what happens to the refracted light? Well, you can't have light refraction more than 90 degrees because it doesn't get out of the surface. And so when we get to the point where the angle of refraction is 90 degrees, then we can't have refraction anymore. And so at that point we say it's the critical angle. Remember at the very beginning I said, and this is the critical angle. I said, wait, let's wait. We're going to have that at the end of the lecture. the critical angle is the angle of incidence, so the angle I would have right here, that would result in an angle of refraction of 90 degrees. Now, if we think this through, if light goes from faster material to slower material, i.e. from air into glass, which direction does it refract? Toward the normal or away from the normal? Toward. If you go into slower material, it always refracts toward the normal. Can you get to 90 degrees if it refracts toward the normal? No. So you can only have this total internal reflection if you're going from a slower speed to a faster speed. And that theta critical, the critical angle is the angle where the refraction would be 9 degrees. If the angle of incidence is bigger than that critical angle, it's just completely reflected. You use the law of reflections, the law of mirrors, to calculate what's going on. If the angle is bigger than that, or smaller than that, excuse me, then I have both the refracted and the reflected. And so I can use the prism as a very efficient mirror. And prisms have historically been used just for that. You had very complicated prisms that people would make to act as mirrors that were very effective. And so this here works to redirect the light straight back, parallel to to how it came in. We talked about that last class period. As long as I have total internal reflection, if it's a 90-degree angle here, it's going to be a retroreflector and reflect it straight back. Or I can do other things with it, but we're out of time, so I have to let you go.